Hey, how's it going, guys? My name's Daniel, aka HashLips. Last time we left off with the Solidity course where I showed you and created my contract.sol and showed you the basic syntax of a contract. We also went over the basics of remix, as well as I showed you how to properly comment your code. This is just an example, so I'm going to keep this example over here, and then we're going to move on to types. Now, whatever we've used in our contract up until this point is perfectly valid Solidity code. But string is not a primitive native type to Solidity. It is there, but it's not as it seems. Strings are actually consisting of bytes all bundled up together that produces this. That's why strings usually cost a lot of gas when using them in your smart contracts. So I would advise to always keep your usage of strings to a minimum, and then rather rely on primitive types such as bools, integers, addresses, and those things. But what are primitive types in Solidity? And how does it work? Well, let's take a look by creating a new file. Now, go and create your file mytypes and mytypes contract. I want you to get used to this syntax, so go and type this out for every single part of this tutorial that we're going to do. This should start feeling like second nature when working with smart contracts. So create your contract little box, because we are going to declare some types in here and explain what they are. Let's have a look at the types in the Solidity documentation. So, types is basically a format of data, and that's how I understand it. You can get a type that is Boolean, which possible values can either be true or false, a 1 or a 0. And with types, what makes types very cool is that we can then eventually use something called logical operators, which you see over here, which we can use in if statements or conditional statements to kind of check data against each other. And that's what I'll explain too, but we first have to look at the basic types we get. Now, for types, we get the type Boolean that you've just seen. This is the type of bool, which can either be false or true, or 1 or a 0, whatever you want to have. Now, when declaring a type, using a type to declare a variable, you can declare variables in different types of scopes, which will be after this section. But just get used to this syntax for now. First, declare your type's data structure. So in this case, it's the Boolean. Then we're going to give this Boolean a name. We're going to call it myBool or myBoolean. MyBoolean can either be declared or not. If you do not declare a type, a variable on the start of a smart contract, it will default to its falsy value or its zero value, if I can put it like that. It will declare itself, in this case, to false behind the scenes. But I'm going to be declaring each one of these variables. Now, you have seen that I've mentioned logical operators, and in here you see an equal sign. These are double equals. This does not mean the same as a single equal sign. The single equal sign basically indicates that we want to put the value, which is here on the right, we want to assign this to this Boolean, to this data type. All right. So we can assign a Boolean type can either be true or false. You cannot put in that, or you cannot put in a string. It will not work. Okay? So basically, we want to use false or true, whatever the case might be. The next data type that I want you to have a look at is integers and unsigned integers. What is an integer? Well, an integer is simply numeric values. And how do we use that in Solidity? You can start off by declaring an unsigned integer for any numeric value that you want to save or store, because that is basically what these variables here at the top is that we are busy declaring. It is storage allocations that we give the program to tell it we want to store my variable, which is a type of Boolean, which starts off as false, in your storage on the blockchain. We will get to scope in just a bit, but let's understand that for now. Let's look at an unsigned integer. You get a uint, which is unsigned integer, and you also get a int, which is just a normal integer, like so. But for the uint, let's go and declare it and call it my uint. And we're going to equal this to a bunch of random numeric values. Now you see that this works perfectly, and this numeric value can actually be quite big because uint at the back of its core converts to a uint 256. This is very important to understand that whatever number comes behind the uint declaration of the type is based on how many bytes it has. This tells us that this unsigned integer value can be and can take up as much storage space as 256 bytes, which is quite a big number. That's also the reason why uint256 are being used to store mappings such as address values of how much money people have in their wallets, how many NFTs exist, and so on. But you get smaller data types, and it's very important to use the smallest one that is the most applicable for your use case. And the reason for that is because gas is quite important in smart contracts. You often hear the term gas, and gas is basically the driving force of executing smart contracts, deploying smart contracts, and it's kind of a reward for the miners to facilitate the blockchain to run. Now, obviously, the more storage you have in your smart contract, the more gas it's going to take, and depending on each little part in your smart contract, it adds up. That's why only use big types like these when it's necessary. You get smaller types of unsigned integers like uint 32, which you can say my uint 32 is equal to a smaller now amount. This is not the actual amounts that it can be. I'm just illustrating this in a visual fashion. We also get uint 16, which is, we can call it my uint 16, which we should definitely make then into a smaller one. You can already see it starting to overflow there, right? So if I give it a bigger number, you can see that it gives us a red indication saying that the literal is too large to fit in a uint 16, meaning that the bytes, there's not enough bytes. It can only handle up to that amount. Not this specific amount. There is a specific amount that each one of these can go up to its maximum to. These are just things I'm typing out. Just take that, a note of that. And then we get a uint 8, which is 8 bytes. Now, 8 bytes is quite cool, and this is something we can elaborate more on. 8 bytes can go from 0, and I'm going to put this in a comment, so I'm going to maybe make it 255 over there, but in a comment I'm going to illustrate that this can go from 0 up to 255, and that's the numeric value that 8 bytes can hold. And how do we calculate this, right? It's called 8 bytes because it's about 8 of the bits, or a bit is calculated in the computer language, and it determines that this can be about 8 of these bytes, or 8 of these bits. I think it's bits, but basically I'll get back to you on that one. But basically what it says is this type can only go from 0 to 255. And how do we calculate that, right? We calculate it by taking the bit, right, and putting a to power sign on it. How do we do that? Let's see. So we can go and say that if we pull up our calculator here, and we go and say that we want 8 bytes, so we need to take a bit to the power of 8, right? So let's take 2, which is a bit, times 2 times 2 times 2 times 2 times 2 times 2, and another times 2, right? 2 to the power of 8 is 256, and then we need to minus 1. And that will give us the maximum value of any of these. So what you can then do is say 2 to the power of 8 minus 1. This will give you the maximum value of 255 for this given data type. So why is it important that we use the correct data type? Well, in Solidity, there's something called Overflow, and this happens to all kind of programming languages if it is compiled, because the thing is, a computer can only handle so many bytes and until it will overflow. Now, in the previous Solidity versions, if this variable was a counter and our program ended up counting above the allowed byte size, then what will happen is it will overflow, and this value would in the background become 0. Sometimes this is the desired effect, and what you can do is actually use in the Solidity code is use the overflow, the uncheck value. So here it is. You can wrap your function in an uncheck, and then it will not do that type check for you in the overflow. It will basically omit it. So you don't only get overflows, but you also get underflows. So a uint cannot go into the minus, then it will be read as well. How do we work with minus values, you might ask? That's where integer values are for. Now we have worked with uints, but you also get integer values. So we can basically go ahead and declare these all as integers. The reason why this will work is because a uint is called an unsigned integer. And an unsigned integer is basically saying that there is no sign in front of the number. And that's basically what it is. So after creating these all into ints, and I just want to rectify this, theoretically, we can put an unsigned or a signed integer now in front of all of these values, and it will not break. Something to note is that yes, this has the capacity of 255, but when it's unsigned, you have to calculate the half of that going into the minus. For instance, we cannot put 255 in here, it will break on an integer 8. You can only go up to 127, because if you cross that line, or 128, because if you cross that line, it will start breaking. This is basically the half of 255, and you can go into the minus, or you can go into the plus of 227, right? Otherwise it will break. So that's basically how it works with a signed and an unsigned integer values. All right, and sometimes you want to have this as a use case to go into the minus, but it's rarely used. And I'm just going to give us a little bit more space over here. Perfect. I think that you guys have grasped kind of what the integers are and the signed and the unsigned types. Now, if you want more information on these basic primitive types, you can go into this these type declarations that Solidity offers and go and read up a little bit more about it. The last type that we want to discuss quickly is the address type. You can see that the address type in the back holds 20 bytes, okay? It's a 20 byte value. So let's go and declare an address type. Let's create some space and write address. Now the address data type is very crucial in Solidity, seeing that everything exists and consists of addresses, especially your wallet address, the smart contract address, and you need to sometimes communicate that. So we can call this my address and equal it to a value. Now, how does that value look if it's not declared from the start, if we just end it right here? The default of an address would be something like 0x and a bunch of zeros. But if we want to declare an address type, we have to set it to the address type like so. This is my address, and this is a perfectly valid address to go into this address field where the underlying type is of address. This is not numeric values, it's a hashed value, and that's why address is a special type that Solidity gives us to use. And this is very good because this means we can do awesome things with it, like make it payable, which we'll get to a little bit later in the series, but basically send money to this address, work with contract address, because this doesn't only have to be a address of a wallet. We can also declare another address and call it my contract address, which can give it any name we want to. So if we were to deploy a contract and we grab the contract's address by clicking on this copy button, this is the actual contract address of the smart contract instance that we've just deployed here. So later on, you will see how we can communicate with other contracts on the blockchain from our contract, and that is a very cool process. That's why the type address is also very crucial. Now, I hope you guys understand this and the way that we work with basic variable data types, which then in turn we declare variables. Variables has a little bit more of a complexity to it. If you look at the contract that we just deployed, you cannot see any of these values, and that's because their scope that they are living in now is private. There are three different scopes that you get on variables. And the three different scopes are public, internal, and private when you declare a variable. Just keep in mind something that I want to note is that when you declare variables directly in the scope of your contract, and how do you determine the scope? Well, anything inside these curly braces that's not inside of another function is the contract scope, all right? And in that scope, everything inside that contract, these variables have access to each other, and also functions will have access to this. Think of scope as a parent. A parent box has gives access to the boxes inside, and the boxes inside has their own variables, and the parent box doesn't necessarily know about those local little things they have in, which we'll get to, but it's just all about scope. So this is on the global scope of a contract. You get a even bigger global scope, which is the blockchain object, which gives you a global variable access to what the blockchain offers us. Things like the block timestamps and so on. We will look further into that main blockchain variable in a separate video, but for now I just want you to understand scopes. So how do we give access to the users that's using our smart contract access to all of our variables? Well, we simply do that by adding the scope public to it, right? We declare the scope of this variable as public. Let's do it for this one, and this one, and this one. We'll leave all of these not scoped, and then maybe we make the address public as well. Once we've saved this, and we then go ahead and delete what we've deployed before, and we redeploy our contract, we will see that we actually get each one of these variables that's declared on our blockchain instance, and we can call these. So I can click on my address, and there it is. It doesn't organize them here in chronological order, but it looks like it does by name, I guess. But anyway, we get each one's value which we can call, and it returns to us. The public scope modifier, if you can call it like that, actually creates an internal getter function, and that's why we get access to it so easily now. Just take that into consideration. I just briefly touched on order. Ordering any of the global variables that you put in your smart contract is very important. It would not make sense if you had the Boolean value stored in between these integer types, as well as, let's take it out there, as well as if an address was declared and you put it in between here. The reason is because when the compiler runs through the code, it has to now do extra work to work out where all these addresses live and what data type they are. Your program will still function as normal, but to optimize it, please try and always keep the different types that you declare inside their respective bubbles, if I can put it like that. Just order them right after each other. For instance, if you had more 256 UN256 variables, go and declare them together like this. This just tells the compiler in a much better way. It just shows red because we have the same variable name, but this tells the compiler that these all are 256 and it organizes it in a much better and performant way. So that is what we get for accessing and also just organizing code a little bit. The next variable that we get is private, not variable, but the variable scope is private, so we can make these two private. You'll see that if we close this program and run it again, that we only still have access to the public variables. What does private mean and why do we not see it? Well, private tells this variable that it can only be used inside of this smart contract. It can never go outside of this box. By default, I think variables are private if you don't declare a state, and that's how you can use them. That means that private variables, other smart contracts can't even call them. But what if we need a type where we want other smart contracts to be able to call one of these variables and have access to it and read of it? How do we give access to another smart contract as well as declaring it kind of private to the users? We have a third one, which is internal. And when you declare something as internal, it basically means that only this smart contract has access to this internal value, as well as other smart contracts that derive or that inherent from this smart contract, I believe, will have access to it. Okay? If you need anything accessing your variables, make it public, as long as it's not sensitive data that you don't want the users to see, but just go and make it public. All right, and another thing, don't store sensitive information here. Anything is visible on the blockchain because everything is in the open blockchain. That's just a side note that I want to mention. But anyway, this is how you work with scope and variables and how you declare variables, giving them names, how to make sure that you fit in the data parameters that a variable allows you to use. And I hope this was understandable enough for you to try this out. In the next part, we are going to carry on with this series and see how we can use these variables with more interesting concepts, just getting a bit closer to understanding Solidity.